Let's start. Welcome everyone to this course Calculus 3. This is the third course of a sequence of 4 calculus courses. And in this course, we will be going over chapters 7, 8, 9, and 10 in the calculus textbook by Laura Tallman and Peter Korn. Okay, we are going to start with chapter 7. Chapter 7 is about sequences and series. Okay, basically we will be talking about fundamentals of sequences and series in this chapter. Okay, let's start with section 7.1. Section 7.1 is about sequences. We will be going over basics of sequences in this sections. Okay. All right, I want to start by giving the definition of a sequence first. Here is the definition of a sequence. A sequence of real numbers denoted by AK, written within curly brackets, is a function from positive integers to real numbers. For each positive integer k, the output AK is called the kth term of the sequence. Okay, what does that mean? That means a sequence AK is a function, is a mapping from set of positive integers to set of real numbers. So your domain is going to be set of positive integers, 1, 2, 3, 4, so on and so forth. Your range is going to consist of A1, the first term, and then the second, A2, A3, A4, so on and so forth. Okay, basically this map, in this map, A1, the positive integer 1 goes to A1, the positive integer 2 goes to A2, 3 goes to A3, 4 goes to A4. Okay, this mapping is what we call the sequence AK. Okay, the sequence AK is this is another notation for the sequence AK. Okay, AK is equal to A1 comma A2 comma A3 comma dot dot dot. This dot 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 means this terms continues forever. Okay. All right. And here I want to note one thing, that is, if the starting index of a sequence is not given, for example, the starting index is not given here. Okay, usually the starting index is written here. If the starting index is not written, that means your sequence always starts at k is equal to 1. That's why you have A1 here. The first term is, you plug in a k is equal to 1 here to get the first term. And then get the second term, you plug in k is equal to 2, so on and so forth. You have A1, A2, A3, okay? But sequence doesn't have to start at k is equal to 1. Okay, for example, this sequence, let's say BK, k goes from 2 to infinity. This time your starting index is 2. Okay, so this is going to be equal to, now you are going to start with k is equal to 2. You plug in k is equal to 2 to get the first term, that is B2. The next term is k is equal to 3. You get B3, B4, so on and so forth. Okay, so as I said, the starting index doesn't have to be 1. Okay, if the starting index is not written, you take always that starting index to be 1. Okay. All right, the other thing I want to discuss here is that I want to discuss what we mean by a closed formula. Okay, for that, I want to take this particular example. Let's say 2k, this sequence 2k. Notice that in this case, your AK is equal to 2k. AK is whatever you put inside these curly brackets, right? So that's your AK. What is the special thing? What is the special characteristic of a sequence like this? One special thing about this sequence is you can always calculate the terms of this sequence by plugging the k value here. Okay, as I said, if the starting index is not given, always the starting index is 1. Okay, this sequence is k is equal to 1 to infinity. That means to get the first term, you plug in k is equal to 1. You can plug in k is equal to 1 in this formula to find the first term. Okay, so the first term will be 2, because 2 times 1 is 2. And then to get the second term, you plug in k is equal to 2. 2 times 2 is 4. So on and so forth. Next term is 6, 8, you get the entire sequence. As you can see, I can use this formula, AK is equal to 2K, to compute the terms of the sequence. Okay, if a formula allows you to compute the terms of the sequence, such a formula is called a closed formula for your sequence. Okay, not all sequences have a closed formula though. Okay, all right, let's move on. Next example I want to look at is this particular example. Find the closed formula for each of the following sequences. Okay, let's try to find a closed formula for the first part, part A. How do we find a closed formula for this one? First of all, notice that if you look at these terms, let's forget about the first term for a second. If you look at the other terms, always your numerator is 1 less than the denominator, right? Here, the numerator is 1, the denominator is 2. In the third term, numerator is 2, the denominator is 3. Again, numerator is 1 less than the denominator. So I'm going to try something like this. K minus 1 in the top, K in the bottom. That way, your numerator is 1 smaller than the denominator. Okay, we want our numerator to be 1 smaller than the denominator, right? Everywhere it is the same. So I try something like this. K minus 1 in the numerator, K in the denominator. That way you have your numerator 1 less than your denominator. Let's see whether this will generate the sequence for us. Okay, what happens if you try K is equal to 1 to infinity? If you plug in K is equal to 1, that will give you 0, right? Because 1 minus 1 is 0. And then plug in K is equal to 2, that will give you 1 over 2. And then 2 over 3, so on and so forth. As you can see, this closed formula generates this entire sequence. Okay, let me remark something here. Okay, one could try a formula like this to start with. One could try a formula like this, because here also, as you can see, if you try a formula like this, your numerator is 1 smaller than the denominator, right? Your denominator is K plus 1, your numerator is K. That means your numerator is 1 smaller than the denominator. But this formula will not generate this sequence. If you try this from K is equal to 1 to infinity, what happens if you plug in K is equal to 1? If you plug in K is equal to 1, you get your first term to be 1/2, right? That's not what you need. Okay. So in any case, if you try a formula like this, if it doesn't work, you need to look for alternative ways. Okay, you need to think of rewriting these terms. Okay, this is the way to rewrite it. Instead of you putting K in the top, you put K minus 1 in the top. Okay, and K in the bottom. That will give you the right sequence. All right. Next part, part B. How do we write a closed formula for part B? First of all, notice that in part B, you have alternative sign. First term is positive, next one is negative, next one is positive, next one is negative, so on and so forth. If the alternative sign is in a sequence, either -1 to the power K or -1 to the power K plus 1 should be in the numerator. If you have alternative signs in your sequence, okay? You need to figure out which one you are going to put in the numerator. Would it be this one or this one? Okay, we'll figure that out. For the time being, let me put -1 to the power K in the numerator. And if it is wrong, I will switch that to this term. Okay, I'll tell you how to figure that out. And then what about the denominator? What should I have in the denominator? Notice that denominator is a power of 2. This is 2 to the power 1, this is 2 to the power 2, 2 to the power 3, 2 to the power 4, so on and so forth. And of course, the first term here, this is actually 1 over 1. 1 over 1 means, this 1 means 2 to the power 0. Okay. So I want to have a 2 to the power something here. What if I have 2 to the power K? Would that work there? It will not, because in the first term should be 1 divided by 1, right? First term should be 1 divided by 1. But if you plug in K is equal to 1 here, you get 2 to the power 1 in the bottom. That is 2. I don't need 2. I need 1. So that means this is not going to work. So I need some adjustment there. The adjustment I need is K minus 1. Now, if you plug in k is equal to 1 here, 1 minus 1, 0, 2 to the power 0 is 1. That's what exactly I want here. Okay. And then what about in the numerator? Is this the right guy? Is this the right term that we need to put here? Well, let's figure that out. Notice that my first term has to be a positive term, right? But if you plug in k is equal to 1 here, what would you get? Minus 1 to the power 1, which is minus 1, right? Minus 1 divided by 1, which is minus 1. That's not what we need. Then you have to realize that this is not the right term. So you have to put the other one. Okay, this should come here. So this should be minus 1 to the power k plus 1 divided by 2 to the power k minus 1. This is the closed formula for your sequence. If you want, you can write k is equal to 1 to infinity. If not, you can just leave it, because if nothing is written, you always assume that the starting index is 1. All right, that completes that example. What about the last part? Part C. Notice that in that sequence, all the odd terms are 0. First term is 0, third term is 0, fifth term is 0, so on and so forth. So I'm going to write a piecewise formula for your AK. AK is the general term, okay? I'm going to write a sequence of this form. My AK is the general term, okay? So here is my piecewise sequence. I'm telling my AK is 0 if k is odd. If my k value is odd, AK is 0. That means if k is equal to 1, this should be 0. Exactly, A1 is 0. And then if k is equal to 3 here, again, AK is 0 because the third term is 0. Okay. And then what about when k is even? When k is even, notice that the second term is 1/3, fourth term is 1/5, sixth term is 1/7, so on and so forth. Okay. As you can see, you have an odd number in the bottom right when k is even. So to get that odd number, I'm going to put 1 over k plus 1. Whenever k is even, if you add a 1 to that, that will make it an odd number, right? So this is when if k is even. Okay, would this work? You can check whether this formula is going to work. What happens if you put k is equal to 1? K is equal to 1 is an odd number, so A1 is going to be 0. If you put k is equal to 2, k is equal to 2 is an even number. If k is an even, this is the formula. You put k is equal to 2 here, you get 1/3. That's the second term. If you plug in k is equal to 3, you should get the third term, right? K is equal to 3 means it's an odd number. So A3 is 0, so on and so forth. You should be able to see you get all the terms in this sequence. Okay. All right, that completes that example. Let's move on. This is the next example that I want to go over. Give the first 4 terms of the following sequence. This is very straightforward. To get the first 4 terms for the first sequence, you have to keep plugging numbers. Notice that since the starting index is not given here, you always start at k is equal to 1. Okay, so the first 4 terms would be, the first term is cosine 1 over 1. You plug in k is equal to 1, of course. And then you plug in k is equal to 2, cosine 2 over 2, cosine 3 over 3. The fourth term is cosine 4 over 4. Of course, you can use a calculator to find the decimal values of these 4 terms if you want. Okay. And then part B, how do you find the first 4 terms? Again, you plug in numbers. Notice that here in this example, the starting index is 2. So you have to start at k is equal to 2 this time. So the first term will be 1 plus minus 1 to the power 2. K is equal to 2. Okay. 2 times 2. I'm plugging k is equal to 2 here, 2 here. That's the first term. To get the second term, I'm plugging k is equal to 3. Minus 1 to the power 3 divided by 2 times 3. The next term would be 1 plus minus 1 to the power 4 divided by 2 times 4. Last term would be 1 plus minus 1 to the power 5 divided by 2 times 5. Okay, these are the first 4 terms of the sequence. Okay, and last one is very similar, so I will leave that as an exercise for you to try. Okay, this is an exercise. You just keep plugging numbers starting from k is equal to 3. Okay. All right, here is the next example that I want to go over. Express the sequence, this given sequence, so that the indexing begins with 1. In the given sequence, indexing begins with 2, right? But we want indexing to begin with 1. How do you handle this? Well, let's use a different indexing variable to write the new sequence. I want my new indexing variable to start at 1. So I will take my new indexing variable to be n. I want n is equal to 1. Okay, I want my sequence to start at n is equal to 1. Now I need to figure out what am I supposed to put here. Here is how you find that. You figure it out. Okay, so you always start with this indexing, the given indexing. The given indexing is k is equal to 2, right? So let me write that equation here. K is equal to 2. I want 1 in the right hand side in this equation because my starting index has to be 1. So to get 1 in my right hand side, what I'm going to do is think of this 2 as 1 plus 1. 1 plus 1 is 2, right? Now I move one of the ones to the left hand side. So this will give you k minus 1 is equal to 1. Actually, this is the same equation as this equation, except for we have written this one in a different way. Okay, you moved one of the one to the left hand side. Okay, so now you introduce your new variable. New variable, we wanted our new variable to be n, right? So I take this left hand side to be n. Always you take your left hand side to be the new variable n, new indexing variable. Okay, so that means n is equal to k minus 1. What does that tell you? That tells you that k is equal to n plus 1. You find your k variable in terms of n. You move this one to the other side, you get k is equal to n plus 1. Okay, now you are almost done. Now all what you need to do is to figure out what to put inside. You go inside here and replace your k variable by n plus 1 because k is equal to n plus 1. Okay, so I'm going to go ahead and replace my k variable by n plus 1. I should have n plus 1 here divided by 2 times n plus 1. Okay, that's going to be the new sequence. Notice that in the new sequence, the starting index is 1. That's what we want. Okay, so that's the proceeding. Okay, that completes that example. Let's move on. Okay, the next thing I want to talk about is recursive sequences. What do we mean by a recursive sequence? Okay, here is the definition of a recursive sequence. A sequence AK is said to be recursively defined if there is some index k, uppercase k, so that for lowercase k greater than that uppercase k, the value of AK is determined by A1, A2 up to AK minus 1. Okay, the equation defining AK in terms of these terms, A1, A2, AK minus 1 is called a recursion formula. Okay, it looks complicated, but what it says is simple. Okay, let me explain what it tells you. It tells you that, for instance, let's say your uppercase k is 3. Then what it tells you is that the first 3 terms are given. A1 is given. Let's say A1 is 1. A2 is say 2. A3 is say again 1. As you can see, if k is equal to uppercase k is equal to 3, the first 3 terms are given. If this was 4, the first 4 terms should be given. Okay, and then you are given a relationship to find the remaining terms of the sequence. Okay, what are the remaining terms? A4, A5, A6, so on and so forth. Okay, a relationship is given. That relationship could take the form like this. Okay, it could take different forms, of course. For example, AK minus 1, AK is equal to AK minus 1 plus AK minus 2. This kind of a relationship is given to calculate the remaining terms of the sequence. Okay, all right. So to get a solid idea about what I'm talking about here, let me walk you through an example. Okay. So this is the, let me erase this sequence so that I can show you, we generate this sequence. All right. So this is, we are going to construct some famous sequence called Fibonacci sequence. Okay. I'll denote that sequence by AK. We are given the way how we should construct the sequence, Fibonacci sequence. Okay. We are given that the first term is 1, A1 is 1, the second term is 1 again. Okay. A1 is 1, A2 is 1. And for K greater than or equal to 3, we are given an equation to calculate the terms. Okay. This kind of an equation is called a recursive formula because it allows you to calculate the terms of the sequence using the previous term. Okay. So now A1 and A2 are given, right? How do I calculate A3? I can use this recursive formula. To calculate A3, I'm going to plug in K is equal to 3. If I plug in K is equal to 3, if I plug in K is equal to 3 in this formula, what do I get? A3 in the left-hand side, and then in the right-hand side, if I plug in K is equal to 3 here, 3 minus 1, 2 is 1. That is A1 plus A2. Of course, if you plug in 3 here, 3 minus 1 is 2. So you get A2. Now, notice that A1 and A2 both are known. They are given to us. So I can plug in those numbers here. This is going to be 1 plus 1, which is 2. Now I know the value of A3. Now, using this value and some previous values, we can calculate A4. To find A4, I'm plugging K is equal to 4. If I plug in K is equal to 4 in this recursive formula, what do I get? A4 should be equal to A2 plus A3, right? You just plug in K is equal to 4 here, K is equal to 4. That will give you A2 plus A3. Now, can we find A4? We can find A4 if you know A2 and A3, right? Of course, you know. A2 is given to be 1 and A3, we just found it in the previous step. You can plug in 2 here, okay? This is going to be 1 plus 2, which is 3. So on and so forth, you can calculate the remaining terms of the sequence using this recursive formula. To find A5, you plug in K is equal to 5 in this formula everywhere. Okay, that will give you your A5 to be actually 5. The value of A5, if you calculate that, that will be 5. Okay, so on and so forth, you can recover all the terms of that sequence. In fact, if you tried to find the terms of the sequence, you should get these terms. These are the terms that you get. Okay, 1, 1, 2, 3, 5, 8, so on and so forth. Okay, this is called the Fibonacci sequence. This is a special type of sequence. All right, that's about recursive formula. And actually, I want to go over one more example about recursive formula. Here is the example. The sequence 1, 1, 1, 3, 5, 9, 17, 31, ... has the property that the first 3 terms are 1. Of course, as you can see, first 3 terms are 1. After that, every term is the sum of the previous 3 terms. Here is the question. Express this sequence by using a recursion formula. How do you write a recursion formula? Of course, first of all, notice that we are given A1 is equal to 1, A2 is equal to 1, A3 is equal to 1, and then we are asked to find the recursion formula. How do we write a recursion formula? We are given that the first 3 terms are 1, and after that, every term is the sum of the previous 3 terms. So my AK has to be the sum of the previous 3 terms. Very previous term is AK minus 1, right? If you have a sequence A1, A2, AK, pardon me, AK minus 3, AK minus 2, AK minus 1, AK, comma, ... Okay, if AK is here, the previous 3 terms are AK minus 1, AK minus 2, AK minus 3, right? So AK should be equal to AK minus 1 plus AK minus 2 plus AK minus 3. This is the recursion formula that you asked to find. Okay. All right, that completes that example. And of course, using this recursion formula, you can calculate, you can see that you can calculate all the other terms. For example, to find the fourth term, if you plug in k is equal to 4 here, 4 here, 4 here, and 4 here, you should be able to see that your third term, fourth term is going to be 3. Because these first 3 terms are given. Okay. All right, let's move on. Okay, the next thing I want to talk about is geometric sequence. Okay, here is the definition of a geometric sequence. A geometric sequence is a sequence in which each term differs from the previous term by a constant multiplicative factor. We will commonly decide to start such a sequence at k is equal to 0. Okay, typically when we deal with geometric series, the starting index is 0. That's the customary that we will be using. Okay, so this is the form of a geometric sequence, general form of a geometric sequence. It is c times, c is a constant and r is also a constant, c times r to the power k. K goes from 0 to infinity. Okay, to recover this sequence, what you do is you plug in k is equal to 0 to get the first term. If you plug in k is equal to 0 here, r to the power 0 is 1. Plug in k is equal to 0. You get c times r to the power 0, which is c, right? Because r to the power 0 is 1. C times r is c times 1 is c. Okay, and to get the second term, you plug in k is equal to 2 here. K is equal to 1, because to get the first term, you plugged in k is equal to 0. To get the second term, you plug in k is equal to 1 here. If you plug in k is equal to 1 here, you get c times r, right? As you can see, you have c times r. To get k, the next term, you plug in r is k is equal to 2. You get c times r squared, and then c times r cubed, so on and so forth. Okay, and here is an example of a geometric series. Okay, say for example, 2 times 3 to the power k. This is times. Okay, this dot indicates time. K is equal to 0 to infinity. This means your sequence will be 2 times 3 to the power 0, comma 2 times 3 to the power 1, comma 2 times 3 to the power 2, comma 2 times 3 to the power 3, so on and so forth, right? And of course, you can compute the terms of this sequence exactly by simplifying this. The first term is 2, the second term is 6, the third term is 8, the next term is going to be not 8, pardon me. This term has to be 18. The next term is going to be 54, so on and so forth. Notice that if you have a geometric sequence, each term differs from the previous term by a constant multiplicative factor. What does that mean? Notice that every term is the 3 times the previous term. Okay, 3 is the constant multiplicative factor in this case. As you can see, this is 3 times the previous term, right? If you multiply the previous term by 3, you get this term. And if you multiply this term by 3, you get the next term. If you multiply this term by 3, you get the next term. Okay, that's what we mean by each term differs from the previous term by a constant multiplicative factor. In this case, that constant multiplicative factor is 3. Okay, or in other words, if you take the ratio between any 2 consecutive terms, it's going to be 3. When you take the ratio, you have to divide the right hand side term by the left hand side term. Okay, 18 divided by 6. 18 divided by 6 is equal to 3, and 54 divided by 18 is also 3. No matter which 2 consecutive terms you take, always this ratio is going to be 3. Okay, that's what we mean by each term differs from the previous term by a constant multiplicative factor. Okay. All right. And then the next type of sequence I want to talk about is the arithmetic sequences. Okay. Here is the definition. An arithmetic sequence is a sequence in which each term differs from the previous term by a constant additive increment d. This time it's a constant additive increment. Okay. And here is the general form of a arithmetic sequence. C and D are constant here. C plus dk, k goes from 0 to infinity. Again, the starting index is 0. Okay, we take our starting indexing to be 0 when we deal with arithmetic sequences in general. Okay, so this means to get the first term, you plug in k is equal to 0. If you plug in k is equal to 0, you just get C, right? So the first term is C. And then if you plug in k is equal to 1, d times 1 is d, C plus d. To get the next term, you plug in k is equal to 2. That will give you C plus 2d, and so on and so forth. Okay. Here is an example of an arithmetic sequence. 2 plus 3 times k. Let's say k goes from 0 to infinity. What are the terms there? Terms are going to be, the first term is, if you plug in k is equal to 0, it's going to be 2. And then if you plug in k is equal to 1, 3 times 1 plus 2, which is 5. And then 8, if you plug in k is equal to 2, you get 8. K is equal to 3, you get 10. Pardon me, this should be 11, right? Dot, dot, dot. Okay, so this is the sequence. What is the special property of this sequence? If you take the difference between any two adjacent terms, that's going to be a constant. That constant is, of course, 3 in this case. Okay, that's what we call the constant additive increment. That constant additive increment in this case is 3. Notice that if you subtract 2 from 5, you get 3. And if you take the next 2 consecutive terms, if you subtract 5 from 8, again you get 3. Go to the next 2 consecutive terms, subtract 8 from 11, again you get 3, right? No matter where you take 2 consecutive terms, the difference is always 3. Okay, difference means the term minus the previous term. That's going to be 3. That's what we mean by each term differs from the previous term by a constant additive increment. Okay. All right. The next thing I want to talk about is increasing and decreasing sequences. Okay. So first, let me give you the definition of an increasing sequence. First of all, recall that the sequence AK means A1, A2, dot, dot, dot. This is the AK term. This is the K plus 1 term, and so on and so forth. It continues forever. Okay. A sequence AK is increasing if AK plus 1 is greater than or equal to AK for all K greater than or equal to 1. First of all, what do you mean by AK plus 1 greater than or equal to AK? Remember, if you look at this sequence, AK plus 1 is the K plus 1 term, AK is the Kth term, right? What this tells you is that always any term is bigger than or equal to the previous term. Okay, the previous term to AK plus 1 is AK. AK is the previous term. Always any term is bigger than or equal to the previous term. If that is the case for any 2 consecutive terms, we say that it's an increasing sequence. Increasing means they are going up, the value is going up. Okay, so this is the condition for a sequence to be an increasing sequence. And then here is the definition of a decreasing sequence. A sequence AK is decreasing if AK plus 1 is less than or equal to AK for all K greater than or equal to 1. Okay, that means any term is less than or equal to the previous term. If any term is less than or equal to the previous term everywhere in the sequence, then we say that it's a decreasing sequence. Okay, Now, let me give you an example of an increasing sequence and an example for decreasing sequence. Here is an increasing sequence: 2, 3, 3, 5, 6, 7, 8. Okay, notice that no matter what two consecutive terms you choose, always a given term is bigger than or equal to the previous term. If you take these two pair, 6 is bigger than or equal to 5, right? If you take these two pair, 3 is bigger than or equal to 3, right? That's the correct statement. 3 is bigger than or equal to 3. Of course, 3 is equal to 3, but it falls the conditions of within the conditions of this inequality, right? So this is an increasing sequence. And here is an example for a decreasing sequence. Okay, in a decreasing sequence, if you take any term, that term is bigger than or equal to the preceding term. Or if you take any term, that term is smaller than or equal to the previous term. Okay, if you take these two terms, this term is bigger than, smaller than or equal to the previous term. If you take these two, this term is smaller than or equal to the previous term. Okay, if that is the case, we say that it's a decreasing sequence. And then we have another definition for strictly increasing and strictly decreasing sequences. Okay, when do we say that a sequence is strictly increasing? Well, we say that a sequence is strictly increasing if you replace this greater than or equal sign by a strictly greater than sign. We say that the sequence is strictly decreasing if you replace this sign by a strictly less than sign. Okay, here is the remark for strictly increasing and strictly decreasing sequences. You basically replace these two signs by their corresponding strict inequality sign. This becomes a strictly greater than. If it is a strictly increasing sequence, this should be strictly greater than. If it is a strictly decreasing sequence, this should be strictly less than. Okay, here are two examples for each of those sequences. This is an example for a strictly increasing sequence. Okay, strictly increasing means every term has to be strictly bigger than the previous term. Okay, if you take, for example, this term is strictly bigger than 5. If you take this term, this is strictly bigger than the previous term, which is 7. If you take this term, this is strictly bigger than the previous term, which is 1. Okay, if that is the case, we say that it's a strictly increasing sequence. And here is an example of a strictly decreasing sequence. If you take any term, that term should be strictly smaller than the previous term. As you can see, 5 is strictly smaller than 6. If you take this term, 2 is strictly smaller than the previous term, which is 3. So on and so forth. Okay, no matter what term you take, that term is strictly smaller than the previous term if it is a strictly decreasing sequence. All right, the next definition I want to go over is a monotone sequence. What do we mean by a monotone sequence? Definition is very simple. A monotone sequence AK is a sequence that is either always increasing or always decreasing. If a sequence is always increasing or always decreasing, that type of a sequence is called a monotone sequence. All these 4 sequences are examples for monotone sequences. They are all monotone sequences. Okay. Of course, this strictly increasing means the sequence is increasing. Okay. Strictly decreasing means the sequence is decreasing. All right, the next thing I want to talk about is eventually increasing sequences and eventually decreasing sequences. What do you mean by an eventually increasing sequence? Well, let me explain that using a graph. Okay, this is the first graph I want to show you. Y-axis represents AK. I'm talking about the sequence AK here. Okay, I represent the Y value, AK value on the Y-axis and the K value on the X-axis. Okay, for example, when K is equal to 1, this is A1. Your A1 is 0.75. Similarly, your A2, when k is equal to 2, you have A2. A2 is roughly about 0.5, so on and so forth. Okay. As you can see, if you look at this graph, initially your AK values are decreasing, right? They are going down as k is getting bigger and bigger. They are going down. But at the end of the day, when k is getting larger and larger, your AK value is going up. It is constantly going up. Okay. If that is the case, we say that AK is an eventually increasing sequence. Why eventually? Because it's not increasing initially. See, initially for smaller k values, your AK is decreasing. And then after some k values, it is going up forever. Your AK value is increasing forever. So if that is the case, we say that this sequence AK is an eventually increasing sequence. A similar definition holds for a eventually decreasing sequence. Here is an example of a eventually decreasing sequence. In fact, for smaller k values, your AK is increasing, but after some k, here in this case, for example, at k is equal to 3, after k is equal to 3, for all the k values, your AK value is decreasing, it's going down. This kind of a sequence is called eventual decreasing sequence. And of course, this one is a strictly decreasing sequence because the terms AK value is going down with k everywhere. What about this one? And by the way, if a sequence is increasing or decreasing, we say that it's a monotone sequence. Okay. If a sequence is eventually increasing or eventually decreasing, we say that it's a eventually monotone sequence. Okay. And if you take a sequence like this has no monotonicity. Okay. Terms are everywhere. It's going up and down. So there is no monotonicity at all. All right, let's move on. The next thing I want to talk about is 3 tests for monotonicity. Okay, I'm going to talk about 3 tests that we can use to determine the monotonicity. Okay, so here is the first part of the theorem. A sequence AK is increasing if it passes any of the following tests. Okay, so the first test tells you that the first test is called the difference test, by the way. That tells you that if this difference AK plus 1 minus AK is bigger than or equal to 0 for all k, then your sequence is an increasing sequence. And the second test, which is called the ratio test, tells you that if all the terms of your sequence are positive and this ratio AK plus 1 divided by AK is bigger than or equal to 1 for all k greater than or equal to 1, then also your sequence is increasing. And the last test is called the derivative test. What it tells you is that if a prime of x is greater than or equal to 0 for all x bigger than 1, given that AK is a function that is differentiable on 1 comma infinity and whose value at any point positive integer k, AK is equal to A of k is equal to AK. What does that mean? That means we have a function A of x, which is a function of x. If you evaluate that function at positive integers, you should recover your sequence. If you plug in k is equal to 1 here, you get A1. If you plug in k is equal to 2 here, you get A2, so on and so forth. Okay. So the bottom line is, if this derivative is greater than or equal to 0 for all x greater than 1, then your sequence is an increasing sequence. Okay. And here is a remark. The obvious analogus of these tests work to determine other types of monotonicity. For example, strictly increasing and eventually increasing. How do you determine that a sequence is strictly increasing? If you want to use the same test, you replace this greater than or equal sign by a greater than sign. If you replace this greater than or equal sign by a strictly greater than sign, then we have a strictly increasing sequence. Or in other words, if a prime of x is strictly greater than 0, then the sequence AK is strictly increasing. Okay. And then eventually increasing means if your a prime of x is bigger than or equal to 0 for large values of x. for x bigger than some number. Okay, then we say that it's a strict eventually increasing sequence. And here is an example that I want to show you. Let's try to apply one of these tests to determine whether this sequence is increasing or decreasing. Okay, and there could be multiple tests that you can apply to determine this, but for this one, let's apply the difference test. Okay, to apply the difference test, notice that in this case, AK is equal to K squared, right? I need to compute this difference, AK plus 1 minus AK. For that, I'm going to need AK plus 1, right? How do you find AK plus 1? If you know AK, well, you simply replace your K by K plus 1, right? You plug in K plus 1 here, you plug in K plus 1 here. You get AK plus 1 is equal to K plus 1 squared. This is going to be K plus 1 squared. Now I'm ready to compute the difference. AK plus 1 minus AK, which is K plus 1 squared minus K squared. If you simplify this, you get 2K plus 1. As you can see, clearly, this is strictly greater than 0. Would you agree with me? That's because you know that if this is a sequence, AK is a sequence, K goes from 1 to infinity, right? So that means K is a positive integer. If this K is a positive integer, this plus 1 is also a positive quantity. This whole thing has to be strictly greater than 0. What does that tell you? That means this is a strictly increasing sequence. Notice that this time we have a strictly greater than sign. If you have a greater than or equal sign, then we can only say that the sequence is an increasing sequence. Now, since this difference is strictly greater than 0, this is a strictly increasing sequence. Okay, let me write AK. The given sequence AK is strictly increasing. Okay. All right, let's move on. And we have a similar theorem for decreasing sequences. Okay, decreasing sequences or a strictly decreasing sequence. All what you need to do is, in this theorem, you reverse the inequalities. You make this inequality less than or equal. You make this less than or equal. You make this less than or equal. Then you get the decreasing version of this theorem. Okay, here is the theorem. The difference test tells you that if this difference is less than or equal to 0 for all K greater than or equal to 1, then your sequence is a decreasing sequence. Ratio test works the same way. If all the terms are positive and this ratio is less than or equal to 1 for all K greater than or equal to 1, then the sequence is decreasing sequence, and a similar thing holds here for the third test. All right, let's move on. Next thing I want to talk about is the concept of boundedness of a sequence. Okay, what do you mean by a bounded sequence? Bounded means the sequence terms cannot be too big and too small, right? That's the intuitive idea of a bounded sequence. Sequence terms of the sequence cannot be too big or too small. Okay, so here is the formal definition. A sequence AK is bounded above if there exists a number uppercase M such that AK is less than or equal to that number for all K. That means we have a number uppercase M such that all the terms of the sequence are less than or equal to that number M. If that is the case, we say that the sequence is bounded above. Okay, in that case, this M is called an upper bound. Okay, here is the definition of being bounded below. A sequence AK is bounded below if there exists a number lowercase m such that AK is bigger than or equal to M for all K. What does that mean? That means we can find a number lowercase m such that all the terms of your sequence are bigger than or equal to that lowercase m. If that is the case, we say that the sequence is bounded below. In that case, we say that this lowercase m is a lower bound for your sequence. Okay. And then And now I'm ready to define what we mean by a bounded sequence. If a sequence is both bounded above and bounded below, then we say that it is a bounded sequence. If a sequence is a bounded sequence, there has to be a number uppercase M such that all the terms your sequence are less than or equal to that number, and there has to be a lowercase m such that all the terms of the sequence are bigger than or equal to that number. That means all the terms of your sequence are line between an uppercase m and a lowercase m. Okay, if that is the case, we see that it's bounded. If it is not, it's not a bounded sequence. And by definition, if a sequence fails to be bounded above, fails to be bounded below, or both, then we say that that is an unbounded sequence. Okay. Now let me show you some examples. Here are the 3 examples that I wanted to show you. Part 1, this is the given sequence. Okay. In this sequence, notice that your AK is 1 over K, right? AK is 1 over K. In this sequence, AK is 2 to the power K. Here, AK is minus 1 to the K times K. Now, I'm going to graph this sequence. When K is equal to 1, you can plug in K is equal to 1 here. K is equal to 1 here to find the first term of the sequence, A1, which is 1, right? When K is equal to 1, this is the value A1. Of course, you have AK on the y-axis. If you plot this sequence, you get a sequence like this. It's going down. It's a decreasing sequence. Okay. As you can see, note that all the, by the way, as K is getting larger and larger, these points are getting closer and closer to the K axis. Okay, or X axis. Notice that all the terms of the sequence are less than 2, right? This 2 is arbitrary. I can even take 3. It doesn't matter. I take this number 2 to be my uppercase M. This will serve as my uppercase M when we talk about bounded above. Okay, that means this sequence is clearly bounded above because I have an uppercase M which is equal to 3, so that all the terms of my sequence are below this number uppercase M. All the terms of the sequence are less than or equal to 2. Not only that, I can even find some lowercase m, some small number. I'll take this minus 1 to be my lowercase m. Now notice that all the terms of my sequence are bigger than or equal to this lowercase m. Okay, that means this is a bounded sequence. All the numbers are less than or equal to this number and bigger than or equal to this number. That means it's a bounded sequence. Or in other words, this is bounded above, both bounded above and below. So it's a bounded sequence. And here is the next example. As you can see, if you plot the terms of the sequence, AK, the AK value is going up with K. That means this is not a bounded above sequence because it keeps going up forever. It's getting arbitrarily large, right? So you cannot find a number M, uppercase M, so that all the terms of your sequence is less than that number. Okay, there's no way that we can find such a number M. So that means this is not bounded above. It's going up. Okay. What about bounded below? Is it bounded below? Of course, yes. Notice that all the terms of this sequence is bigger than or equal to this number. Say this is minus 1. Lowercase m is equal to minus 1. Then clearly all the terms of this sequence are positive. That means all the terms are bigger than or equal to minus 1. That means this sequence is bounded below. But clearly it's not bounded above. Okay. If one of these fails, if one of being bounded below or bounded above is going to be fail, then it's an unbounded sequence. So this sequence is an unbounded sequence because it's not bounded above. What about this sequence? This is neither bounded below or bounded above because in the positive side, you have your value of the sequence is getting arbitrarily large. So you cannot find an uppercase M such that all the terms of your sequence are below that number. They are getting higher and higher. Okay. Similarly, your sequence values are getting negatively large, arbitrarily large. So you cannot find a lowercase m so that your sequence terms are bigger than or equal to lowercase m. So this is not a, again, this is an unbounded sequence. This is neither bounded above or bounded below. All right, let's move on. Now let's work on this example. Determine whether the following sequences are bounded and or monotonic. Let's work on the first one. What about the first one? Would that be a bounded? Let's deal with the monotonicity later. Would that be a bounded sequence? Well, it is going to be a bounded sequence because first notice that sine k is always less than or equal to greater than or equal to -1, less than or equal to 1, right? That means sine k over k greater than or equal to -1 and less than or equal to 1, right? If you divide this quantity, which is between -1 and 1, by a quantity greater than or equal to 1. This k is a quantity which is greater than or equal to 1, right? If you divide this quantity by a quantity greater than or equal to 1, again you get a quantity between -1 and 1. Okay? As you can see, all the terms of this sequence, are stuck between -1 and 1. That means the sequence is bounded below and bounded above. Of course, this will serve as your lowercase m. This will serve as your uppercase m. All the terms of your sequence is less than or equal to uppercase m and greater than or equal to lowercase m. That means your sequence is bounded. So your sequence sine k divided by k is bounded. Okay. All right. What about monotonicity? This sequence is clearly not monotone because this sign, even though this denominator, let me go here, even though this denominator is always positive, this sine k changes the sign, right? It becomes positive, sometimes it becomes negative. Okay. So that means it's going up and down, right? The values of the sequence are positive, negative, positive, negative, positive, negative. They are going up and down. So it's not monotonic. If it is monotonic, either it should be going up or it should be going down, right? So it's not monotonic. Sine k over k is not monotonic since sine k changes the sign. All right, that completes that example. Now let's go over the next example. Okay, next let's look at part B. To analyze part B to get the monotonic properties, what I'm going to do is I'm going to use the derivative test. Okay, remember recalling the derivative test. It is the derivative test. If your a prime of x is bigger than or equal to 0 for all k x greater than 1, then our sequence ak is an increasing sequence. Okay, and of course if it is less than or equal to 0, it's a decreasing sequence. And a strictly increasing and strictly decreasing sequences are defined the same way. Okay, by replacing this greater than or equal to sign by strictly greater than, and less than or equal to sign by strictly less than. Okay, to apply the ratio test, I'm going to take this by looking at this sequence k to the power 3 divided by e to the power k. I'm going to define the corresponding function. I'm going to take f of x to be x to the power 3 divided by e to the power x. So I replace this x by I replace this k by x, the variable x. That way I get f of x is equal to x to the power 3 divided by e to the power x. Okay. Notice that here, f of k is exactly the kth term of the sequence. F of k is k to the power 3 divided by e to the power k. That's exactly the kth term of the sequence. Okay. To apply the derivative test, what do we have to do? We need to check the derivative, right? Well, to check the derivative, first of all, I have to find the derivative. If you find the derivative, you will see that it's calculus 1. I'm not showing the steps here. F prime of x is going to be x to the power 2 times e to the minus x times 3 minus x. Okay. Notice that if you look at this f prime of x, it is positive. F prime of x is positive if your x is less than 3. Look at this factor. These two terms are positive. These two terms are positive anyway, because we are focusing on x values which are bigger than 1. Remember that theorem requires us to only focus on x values bigger than 1. For x bigger than 1, these two values are positive, and here is where you have a sign change. Okay, when x is when x is less than 3, your f prime of x is bigger than 3. When x is bigger than 3, your f prime of x is less than 3. Okay, that means for large values of x, for all x values bigger than 3, your derivative is negative. Derivative is negative means from the derivative test, your sequence has to be decreasing eventually, because your derivative is less than 0 for x bigger than 3. Okay, so this is an eventually decreasing sequence. By derivative test, I'll write dt for the derivative test. AK, this is AK, okay? Here, let me write AK is equal to k to the power 3 divided by e to the power k. AK is eventually decreasing. All right, so we have the monotone property. What about the boundedness? How do we determine whether it's bounded or not? Well, first of all, notice that this function has a maximum by the first derivative test. Okay, so how do you find the maximum? You set the derivative to 0 and find the zeros of the derivative and use the first derivative test, right? From the first derivative test, you should be able to see that this function has a maximum by first derivative test in calculus 1. In calculus 1, f has a maximum at x is equal to 3. Okay, that means this function has a maximum at x is equal to 3. What does that tell you? That tells you that the maximum value of this sequence, or this one, occurs when k is equal to 3. Because the sequence is just obtained by plugging positive integers here, right? So then if the maximum value of this function occurs at k is equal to x is equal to 3, then the maximum value of this sequence should occur when k is equal to 3, right? So the maximum value, let me add a page here. So maximum value of the sequence is, you plug in k is equal to 3. 3 to the power 3 divided by e to the power 3. That is the maximum value. Okay, and also notice that means all the terms of your sequence are less than or equal to this number. That means AK is less than or equal to that number, e to the power 3, for all k. Okay, and also notice that this sequence is a positive sequence. All the numbers are positive because k is a positive integer. This whole thing is positive. Always it's a positive number. That means all the terms are greater than or equal to 0. Your AK is always greater than or equal to 0. This tells you that your sequence is bounded above. This tells you that your sequence is bounded below. This tells you that your sequence is bounded below. That means your sequence is bounded. If a sequence is both bounded below and bounded above, it's a bounded sequence. So AK is bounded. Done. Okay. All right. What about the next part? Let's go to part C. For part C, we can use the difference test. Okay. First of all, notice that AK is equal to k squared minus k. Then you can immediately calculate AK plus 1, which is k plus 1 squared minus k plus 1, right? To calculate AK plus 1, you replace your k by k plus 1 here. This is the formula for AK. You replace your k by k plus 1 to find AK plus 1. That will be this, right? And then you calculate the difference. AK plus 1 minus AK. This is going to be equal to k squared, pardon me, k plus 1 squared minus k plus 1 minus k squared minus k. What would this give you? If you compute this difference, you will get k squared. I think you will get 2k, okay? You're going to get 2k. Notice that since you are running starting index is 1, k is equal to 1 to infinity, this quantity is strictly positive. If this difference is strictly positive, that means your sequence is strictly increasing. Okay, AK is strictly increasing. By the way, here AK, your AK is in this case, what is AK? That's the general term, k squared minus k. Okay. All right. What about the boundedness? Well, you can easily see that it is unbounded if you write your term AK this way. K squared minus k, which is equal to, if you pull out a k, you get k minus 1. Now, as you can see, when k is equal to 1, this value is 0. When k is equal to 2, this is 2 times 1. When k is equal to 3, the first term is 0, second term is 2 times 1. And then if you plug in k is equal to 3, you get 3 times 2, and then 4 times 3, and then 5 times 4, so on and so forth. As you can see, terms are growing, right? They are getting larger and larger. This is times, by the way. 5 times 4. Okay. See, this is 4 times 3, 5 times 4, then 5 times 6, so on and so forth. These terms of this sequence are getting arbitrarily large as k is getting larger. Okay, so it's not bounded. AK is not bounded. The sequence AK is not bounded. All right, let's move on to the last part of the example, the ratio test. Okay, part D, for the part D, to find the monotone property, I'm going to use the ratio test for this one. Okay. Well, first of all, I want to introduce a new notation here. This is 10 to the power k, which you are familiar with. But what is this notation? K, this exclamation mark. That notation means k factorial. We say that it's k factorial. or factorial k. Factorial k is defined by 1 times, 2 times, 3 times, dot, 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 3, 4, 5, 6, that means, and then the last term should be k. The product of first k terms, 1 times, 2 times, 3 times, all the way up to k. And then you should be able to tell me what do we mean by k plus 1 factorial. That's going to be 1 plus 1 times, 2 times, 3 times, all the way up to the term k plus 1 this time, because the last term should be k plus 1 according to this definition, right? If this was k, the last term is k. If this is k plus 1, the last term is k plus 1. Okay, that's the definition. Okay, with that in mind, let's try to determine the monotone properties of this sequence. Okay, for that, as I said, I'm going to use the ratio test. To use the ratio test, I have to identify my AK. My AK is, I take my AK to be this inside term, that is 10 to the power k divided by k factorial. Now, to apply the ratio test, I need to compute this ratio, AK plus 1 divided by AK. Remember, in the ratio test, I need this ratio, right? If this ratio is less than or equal to 1, then it's a decrease in sequence. If it is greater than or equal to 1, it's an increase in sequence. All right, so how do we find AK plus 1 divided by AK? First of all, notice that you can find AK plus 1 by plugging k plus 1 in this formula. You replace your k by k plus 1 here. You replace your k by k plus 1. You put k plus 1 here. That will give you this term. Your AK plus 1 is exactly 10 to the power k plus 1 divided by k plus 1 factorial. And your AK is, of course, this one. It is same thing as this. Okay. Now you need to simplify this using the reciprocal rule. Okay. If you simplify this quantity using the reciprocal rule, what you do is basically, by reciprocal rule, this quantity, I'll show you a little bit of simplification. That quantity is going to be equal to 10 to the power k plus 1 divided by k plus 1 factorial multiplied by k factorial divided by 10 to the power k. Okay. Now you can put this one over here. K factorial is 1 times, 2 times, all the way up to k. And then k plus 1 factorial is 1 times, 2 times, 3 times, all the way up to k plus 1. Let me show you a little bit more simplification. First of all, notice that there is a cancellation here. You have 10 to the power k here. You have 10 to the power k plus 1 here. So 10 will be in the top. That's going to be 10 in the top. And in the bottom, you have 1 times, 2 times, 3 times, all the way up to k plus 1. And in the top, you have 1 times, 2 times, 3 times, all the way up to k. So all the first k terms will be cancelled here. The remaining thing is k plus 1. This k plus 1 will remain in the bottom. Okay, will be remaining in the bottom. So it will give you 10 over k plus 1. That's how I came up with this 10 over k plus 1 by simplifying. Okay, now how do we determine the monotonicity? Is it monotone? Monotone means either increasing or decreasing. Eventually monotone means eventually increasing or eventually decreasing. Well, notice that here, this ratio AK plus 1 over AK is bigger than or equal to 1. That ratio is bigger than or equal to 1 if your k is between 1 and 9. If this k is between 1 and 9, this is bigger than or equal to 1. If your k is bigger than 10, if this k is bigger than 10, then this ratio is less than 1, right? Okay, this ratio is less than 1 if your k is bigger than 10. That means this is a eventually decreasing sequence. Of course, if this ratio is less than 1, it's a decreasing, but it is less than 1 only for k bigger than 10. That means this is an eventually decreasing sequence. In this case, AK is an eventually decreasing sequence. Okay. And then to determine whether it is a bounded sequence, I will leave it as an exercise. It is very similar to the previous part. Okay, leave it for you as an exercise. Try to follow the same ideas we used in the previous part. And the next example that I want to go over is this one. Discuss the monotonicity and boundedness of the sequence. This is the given sequence. When you work with a sequence like this, the first thing that you need to do is you need to find the general term of the sequence. That is the challenging thing. Okay, there is no clear rules for you to find the general term, but you need to somehow find some sort of a connection to each term. Okay, so clearly you should be able to tackle the top, right? The numerator. Numerator is going to be powers of 2. So 2 to the power k has to be in the top. And in the bottom, if you carefully observe, you have in the kth term, you should have 1 times 3 times 5 times 2k minus 1. The last term should be 2k minus 1. Okay, as you can see, you can justify that this formula is correct by plugging numbers. If you plug in k is equal to 1, you should get the first term. If you plug in k is equal to 2 here, you should get the second term, so on and so forth. Okay. All right, now again, I'm going to apply the ratio test to determine the monotonicity in this sequence, for this sequence. Okay, so for that, I'm going to have to calculate ak plus 1 divided by ak to apply the ratio test. Ak plus 1. How do you find ak plus 1? You know the formula for ak, right? All what you do is you put k plus 1 here, k plus 1 here, k plus 1 here. That will give you ak plus 1. This is exactly your ak plus 1. Okay, and then of course ak should be in the bottom. This is your ak. And then you need to do the reciprocal rule to simplify this one. Okay, if you do the reciprocal rule here, you are going to come up with this expression, 2 divided by 2k plus 1. Clearly, this is strictly less than 1. Would you agree with me? Notice that k is a positive integer. If k is a positive integer, that means k is equal to, k can be 1, 2, 3, 4, right? So that means this number is always bigger than or equal to 3. But in the top, you have 2, right? So this whole thing has to be less than, strictly less than 1. What does that tell you? That tells you that ak, by ratio test, of course, by ratio test, the sequence ak is strictly decreasing. What about the boundedness? If this sequence is strictly decreasing, every term is less than the previous term, right? That means the first term has to be the biggest term, right? In this sequence, first term has to be the biggest term. So A1, pardon me, A1 has to be the biggest term. Okay, this is not AK, A1, okay. But notice that all the terms of the sequence are positive, right? That means these terms of the sequence are bounded below. So your AK is always less than or equal to 2, which is the first term. First term is 2. And AK is always greater than or equal to 0, because all the terms of your sequence are positive terms. Okay, so your AK is always greater than or equal to 0. This means your sequence is bounded above. This means your sequence is bounded below. What does that tell you? Sequence is bounded. Bounded above. This means bounded below. that means that implies sequence is bounded. Okay, that completes that example. All right, let's move on. This is the last thing that I wanted to talk about, to give this definition of a least upper bound and greatest lower bound. Okay, what do you mean by a least upper bound? By now you know what we mean by a upper bound, right? For example, if you take the sequence 1 over k, we just observed this in a previous example. If you put your ak here and k here, you saw that this was a sequence like this going down. This is 1, of course. When k is equal to 1, your ak, a1 is 1. You plug in 1 here, right? K is equal to 1. Okay, we saw that this was a decreasing sequence, and we also saw that 2 is an upper bound, right? If you take 2, all the term 2 is somewhere here. All the terms of your sequence was strictly less than 2. All the terms of your sequence is below 2. That means 2 is an upper bound, right? But notice that even if you take 1.5, 1.5 is also an upper bound, right? Because this is the biggest term. A1 is the biggest term, which is 1. In this case, A1 is 1. That is the biggest term in the sequence. The second term is little less than that. Third term is even less than that. So on and so forth. Okay. So as you can see, 1.5 is an upper bound. Even 1.2 is an upper bound. Likewise, what is the smallest upper bound that you can get here? For this sequence, for this particular sequence, what is the smallest upper bound? As you see here, 2 is an upper bound, 1.5 is an upper bound, 1.2 is an upper bound, 1.1 is an upper bound, 1.0001 is an upper bound. Likewise, what is the smallest upper bound that you can get? The smallest upper bound that you can get is 1, right? 1 is the smallest upper bound. So 1 is given a special name. That smallest upper bound is given a special name that is called the least upper bound. Okay, that's the idea of least upper bound. The least upper bound in this case for the sequence AK, in this case, is 1, because 1 is, all the other terms are less than or equal to 1. Okay. Similarly, we have a definition for greatest lower bound. Okay, a lower bound m, lowercase m, that is greater than or equal to all the other lower bounds for a sequence is the greatest lower bound for the sequence. Okay, similar example can be given for this one also. I'm not going to explain the second part. It is very similar to the definition of justification is very similar to the definition of least upper bound. Okay. All right. With that, we conclude section 7.1. I'll see you next time.